This is quiz number 3 in our collection. And deals with half-life and molecular rate theory. Okay, and the reaction. The time required to reduce the concentration to 1/2 the original concentration is called half-life. Exactly right. It's basic definition of half-life. If we examine that in graphic context, as a function of time, concentration changes. And here we find that the first order reaction will follow this typical trend, okay, as far as changing concentrations as a function of time, the rate issue. If we specify this point as the initial concentration, then the distance, if you visualize it, 1, 2, 3, 4, 5, 6, 7, 8, 9, so that'd be 1, 2, 3, 4.5. That point right there would represent the original concentration divided by 2, and if we extend it over to the curve and then straight down here, that is half-life. Time it takes to cut the original concentration in half. One of the points that I will make in here, all half-lives are constant. Okay, now they'll exponentially compress as you come down here. The second half-life will be, say, about right in there. That's C sub O over 2, and then half of that, or C sub O over 4. Now, one other thing to remember is these concentrations that are specified, regardless of whether it's half-life or not, after a decrease in concentration, in problems they refer to remaining concentrations. So the half-life equation is derived from the first order decay equation, which describes this trend. This equation and these concentrations that would show up in questions on an exam, most likely, if they don't specify anything else, will refer to the remaining concentration. Okay? And of course, that's E choice. What's in our question? Any questions on that? We're going to work a bunch of problems today on a lot of this stuff. Okay. Number 2. If the half-life of a compound is 10 days, okay, so they're giving us half-life equal 10 days. How long would it take for 75% of the compound to decay? Well, using the same idea, it's easier to this looks better, I guess. So you have a change in concentration, and molar concentration here, and going here is time. And again, we're starting 100% and following this trend. Okay. By definition, the half-life is the time it takes to cut this original concentration in half, and that would be the C sub O right here. So in halfway, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7 and a half. I guess looks like about right. Maybe a little higher. Now, let's say that's the C sub O over 2. I'm just counting. You get the point. Coming over here and straight down. Okay, and that's 10 days. Now, when we talk about this 10 days, this. Come over here and do it this way. We're talking about from this starting point to this point is 10 days. Refers to this period of time right here. Now, the one thing you need to remember is half-lives are constant. Half-life, first half-life, second half-life, same. So, half-life is half-life is constant. We just call them second half-life, third half-life, fourth half-life positions. Now, from a problem-solving and context point of view, if they ask you how long it takes to go from an initial concentration to one of the half-lives down here, you add up all the half-lives. And that's what this problem initially refers to. It says, how long does it take for 25% to remain? That is, 75% is consumed. So we'll split this one in half right here, and we'd have 1/2 of that concentration, like that, which is, of course, C sub O over 4, and that represents 25% remaining at that point right here. And so we come across here, hit the graph, and then straight down to here, and that's the second half-life. Second half-life point, which is 2 times the first half-life. And so if we take that into consideration, the time to go from here to the second half-life is also 10 days. But the total in here from start initial concentration to record 25% remaining is 2 half-lives, which is equal to 2 times 10 days, and of course 20 days. So be wary of how the problem is worded. Are they asking you for how long it takes or the total time, or how much is a given lifetime? And in some problems I'll pop in there and say the first half-life is 15 minutes. What's the third half-life? Now in that context, it's still 15 minutes. Okay? I didn't ask you how long it took to get there. Okay, please make a note of that. If I'm still not making sense, check with me, because it's very important. A number of questions will pop out of the woodwork on that issue. D choice in that. Okay? For any given first order process, half-life can be assumed to be constant. We're emphasizing that in the last 2 questions that we talked about. So we'll just make this a short recess here and And that would be a choice right there. And the illustration I gave a moment ago here kind of shows that 10 days, 10 days. But if they're asking you for how long it takes to cover all of those half-lives, you'd have to add all the half-lives together. One comment here is that I'm focusing on first-order reactions because in the world, problems and things, first-order reactions are the most dominant, 99% of them. But keep in mind there are zero-order equations for the integrated rate form and second-order integrated rate form second-order equations. So you could do the same thing, develop half-life equations and solve problems around zero-order and second-order equations. You won't see that on your exam. I focus exclusively on the first order. If you want to know more about the zero, important, check with me after classes or something, and I'll be glad to go over it with you. Okay.
Later on, will we be going over second order and
zero
order? Or?
I will not develop a second order or zero order decay expression, but you are responsible for your first or all of the orders in the rate laws, like when we have rate law tables and things where you figure the trends. This is not a trend issue, okay? Okay, let's see if I'm back on the screen now. Number 4, this is kind of a stretch problem, and it's more of an intuitive type of answer. And you'll see more of it as we cover it today in kinetic molecular theory. The rate constant for the solution phase decomposition of dinitrogen pentoxide is 0.146. So we get this dinitrogen pentoxide in a solution reaction going to 2NO also in solution and gives off half mole of O2 gas in the process, and its K value is identified as 0.146 seconds to the -1. Now some of the things that you may or may not know, or you should have brought from the first course in chemistry, when an equation is given like this, it's assumed to be a standard state equation. All standard state equations are assumed to be at 25 degrees Celsius and atmosphere. This is referred to as the standard state or standard thermodynamic state. In thermochemistry in Chem 1, this is a big issue when I teach the course anyway. Because anytime that you go into a problem in a book, they're not going to tell you the conditions around it, okay? And you have to work a gas law problem or something. You start mentally with 25 degrees in 1 atmosphere, whatever. We also learned in the context, so this, well, I should have said this, so this is at 25 degrees C. So if you increase the temperature of your reaction, according to the rate factors, which are C, A, N, T, C, concentration, area, nature, temperature, and catalyst. If we change any one of those, the reaction rate will change. The rate constant will change. Okay? I asked you, said, well, if the temperature goes up, what does the rate do, or rate constant do? It will go up proportional to the increasing temperature. You don't know if it's linear or not. They don't follow first order trends. So for changing temperatures, rate constant follows temperature trend, but is not necessarily linear. So in this particular case, we'll see more about this today. B choice on that one. We'll learn more about that today and as I expand on it. The last one, assuming the following graph illustrates a first order decay. First order decay graph again. Okay, so there is a first order trend. So it says, assume the following graph is illustrates first order decay trend with reactant concentrations decreasing with respect to time. Which of the following expressions would one use to calculate the half-life of the first order reaction following the same trend? All of them. I'll show you. Now, if you'd gone over the half-life and derivations that I gave you and went over the problems in the video, you'd have known that. Okay, it was clearly in there. Okay, so for the half-life equation is basically derived out of this expression right here. Half-life assumes C sub O over 2 is your C final, and that's C final. So we can write C sub O over 2 equals C sub O e to the minus KT, and now that is a half-life. When we assume this condition here. Well, if we divide both sides by concentration, initial concentration goes away. Doesn't matter what the concentration is. If it's decreased, goes to the next half-life, still the same half-life time. We have 1/2 equal e to the minus KT to the 1/2, like that. Now, I can take the reciprocal of both sides. You can do anything to an equation, math equation, but you got to do it to both sides. So I'm going to take the reciprocal of both sides, and I wind up with 2 equals e to the KT, like that. Now, I want to get rid of the e function. In order to get rid of an e function, you take the natural log, because that's the base of natural logs. So ln of 2 is equal to ln of e to the KT, like that. And as a result, we have ln of 2, which is 0.693, to equal, that should be 1/2 right there, KT to the 1/2. Number of problems will show up using that equation right there. Okay? Okay. Now the ln, all right, we could come over here and let's see, I'll get that second one. From here, you can divide both sides by C sub O, you have C over C sub O, ln of that is equal to the ln of e to the minus kt, which simplifies to minus kt, like that. So we didn't take the reciprocal at this point. But the problem says if you have appropriate data, then you can use this and this together to get it. Well, your appropriate data would be half of the original concentration, and T would be assumed to be a half-life at that point. And down here I showed you is 0.693 to T to the 1/2. This is the one you should memorize and use in majority of the problems that you're going to be facing, numerical problems that we're going to be working with. So I gave this to emphasize that a lot of times you will need to use one form of the half-life equation versus another. There. Okay, B choice.